All right, the last part of the lighting lecture, part 3, let's put it all together into a pixel shader. This diagram shows all the vectors that we've been talking about. These are all the vectors we're going to need for our Phong lighting equation. This little circle right here at the bottom, that represents a single pixel that we are going to be lighting. So that is the location in world space of the pixel. This sun looking thing, this is the light source. So we're assuming like a point light source for this diagram. That is the location where the light is coming from. This eyeball looking thing, that's the viewer. In our case, that's the location of the camera. So where do we get all these things? The location of the light source, we're going to put that into a constant buffer. The location of the camera, we have that also in a different constant buffer. We uploaded it with the rest of our camera matrices, and I may have mentioned in that lab, we weren't using it yet, but we're going to need it. Now's when we need it. We need it now. So we should have the camera's position in world space in a constant buffer, the light's location in world space in a constant buffer. Where are we going to get the position of the pixel in world space? We don't have that right now. But back in the vertex shader, you briefly did have the world position of the vertex, right? When we did the vertex shader, the first thing we did, we took the vertex position from model space into world space, and then from world space into screen space or projection space. All we need to do is take that world space that you had and pass that to the pixel shader. That will give it the world space of the vertex, and the GPU will interpolate that as it rasterizes to give you the world space of our pixel. So if you have the world space of the pixel and you have the location of the light source, you can subtract to get the L vector. Don't forget to normalize that. You can subtract from the camera's location to get the V vector. Well, again, don't forget to normalize. Okay, so that's those two vectors. How about this N? The N vector is the normal in world space at that pixel. Where did we get that? We should have that in the vertex shader. We have the normals of the vertices in model space, and we transform them into world space. Pass that on through to the pixel shader, and the rasterizer will interpolate that for us. Watch out. When it interpolates a normal, it will not automatically keep that normal as unit length. You'll have to re-normalize the normal in the pixel shader, and that is because it is an interpolation between maybe the two vertices or three vertices that it was interpolating between. Maybe they had unit length normals. That doesn't mean that after the interpolation it's still unit length. So you need to normalize the normal in your pixel shader. So now we've got the normal, we've got the L vector, and now the last one we need is the R vector. We get that just by reflecting the L around the N, just like we did in the Pong labs back in 380. HLSL has a built-in reflect function that you can use for this. The only caveat is that they assume that the L vector you were using is going to come in, is coming in towards the pixel and then gets reflected out like this. Whereas in our diagram, we have the L pointing outward, right? So you just need to put a minus sign on that L so that it reflects to get the R that you want to match our diagram. Okay, that's everything you're going to need. Let's take a look at what the full equation is so we can then type that into the pixel shader. Here's the full lighting equation, and I think you'll agree that's some ugly looking math, but when we break it down, it's not so bad. When you write this into a pixel shader, let's break it down into part by part, and don't try to write this all out on one line. Writing it all on one line like that is going to cause bugs. The most obvious problem with doing that is it's very hard to debug. So we're going to want to, when it doesn't work, and say, oh, my lighting isn't working, what's the problem? We're going to need to break it down into little piece by piece and say, how about this part? How about that part? What if you take out that part? And so you don't want this crammed all on one line. But the full equation here, written on one line, in math words, in math-ese, here it is. What are all the terms? This C vector is the final color. That's the color you're going to get as you're going to return that from your pixel shader. That's the color that we got. The A vector, that's the ambient term. So that's, like we said, we're just going to add that on. So you can add it at the beginning, you can add it at the end, whatever, just add it on. This big old sigma is a sum. It means sum over all the lights. K is the number of lights. There it is. K is the number of lights. And I'm going to use the subscript I for light number I. So starting with 0, let's say we have 5 lights in our scene. We'll go 0, 1, 2, 3, 4, and that'll be our 5 lights because, you know, we count from 0. All right, what is C sub I? That's the color of the light. So you might have multiple lights. They might be different colors. The color of that light. What is D? D is the diffuse color of the material. And then here's that dot product of the normal dotted with the light, the direction to the light, that should be here, direction to light number I. And that's our diffuse term. In the Phong, remember we had the ambient, the diffuse, and the specular, those 3 terms. Now the ambient, there's not really need to have multiple ambient lights, probably, so we don't have a summation for that. We'll just throw that on. All the different lights will have a diffuse and a specular term, one by one. All right, so we'll do the diffuse, which is we do this dot product, and we multiply the dot product times the diffuse color. Great. How about specular? We will do this dot product, which is the R sub I, which is the reflected vector. Remember, we take the incoming light direction and reflect it. And the V. V is the direction to the viewer, or to the camera. Raise that to the power gamma. Remember, what was gamma again? Gamma was the specular power of that material. So that's the specular light. And then we multiply times the specular color of the material. Add those 2 terms together, and then we can multiply that times the light color. Or, you know, you could break this out. I like to break it out as diffuse and specular as 2 separate equations. I'll do my dot products as separate lines so that I can have, you know, breakpoints, and I can turn things on and off to see what is working and what is not working. Okay, something that is not on the slide, we're going to talk about it in the lab, but I want to talk about it with you right now as well, and that is these dot products. Now, remember I did my hand, and we talked about the dot product, right? When my hand is pointed towards the light, the dot product between the normal of my hand and the direction to the light is going to be 1.0, and I'll get maximum brightness. And then as I tip it down, I get less and less bright until when they're absolutely perpendicular, I get 0 brightness. But then what happens if we keep going? What happens if I take my hand and point it, like actually pointing away from the light? That dot product will become negative. And we don't want a negative light. This is the dot product I'm talking about right here. If that dot product becomes negative, that would represent a negative light. A negative light would be if I shine that, let's put my hand up. If I shine a bright light on here and it's negative, it will pull light out of the back of my hand. And if I dim the light, it'll pull less light out of the back of my hand. That doesn't make any sense. And so negative lights are bad. Because of that, this dot product isn't shown on this slide, but we need to clamp that so that it does not go negative. So we'll use probably the max function in HLSL to say, when you do this dot product, make sure the dot product does not go below 0. It can go from 0 to 1, but it cannot go negative. Same thing with this dot product. If you have a negative specular highlight, you'll get an inverted highlight on the negative side, and you don't want that. The telltale sign of a negative light is that it's the opposite color or the color complement. For example, if I have a green light in my scene and I forget to clamp this dot product and I let the dot product go negative, it will subtract green from my surfaces. What does it look like to subtract green? Well, white is 1, 1, 1, red, green, blue, right? So if we subtract the green, we have red and blue, right? And so if you see your objects turn purple because of a green light, when we get to it, we're going to have a green light in the scene near the starting point. And what you'll see is that the character will be lit green, except it'll be purple in the shadowy areas. And that's because the green light has been subtracted from white, and that will leave purple. So if you see purple shadows in a green lit scene, that's a clear indicator that you forgot to clamp against 0. Same thing for these speculars, so don't forget that. All right, so let's talk about applying the lighting equation we just talked about. The first, maybe your first pass at it is to apply that calculation in the vertex shader, light each vertex, and then pass those vertex colors through to the triangle corners and let the rasterizer interpolate it. This is what that looks like if you do that. You can see that this is a sphere that was modeled, and we've got the wireframe turned on so that you can see the triangles that it's made out of. But even without that, you can very clearly see this sort of, the specular highlight on the sphere has turned into a hexagon with a very bold, obvious starburst pattern on it. That is caused by the interpolation of the colors. Why is that? The thing is, these lighting equations that we just showed are not linear. So that means that if we allow the GPU to do a linear interpolation across the triangle, we're going to get a linear looking interpolation, and instead of that nice round look we wanted, a circle is not linear, right? We want a circular highlight here, but because the triangles are going to do a linear interpolation, we're going to get a very square looking, hexagonal looking highlight, and it doesn't look very good. Okay, so what can we do? One way to fix that is to make a lot of triangles, increase the tessellation. So here we've just got another sphere, and on the video you probably can't even tell, but it sort of looks speckly, maybe looks like a kickball or something. That's because that's the wireframe. If you look at the edge, you can probably tell that it's very smooth on the edge. It's because this is just like a million triangles. So by having so many triangles, we can see what the highlight is supposed to look like now. It's supposed to look very round, and we get this nice clean round thing because we have so many vertices, right? But that isn't really what we're going to do. What we actually do is do the lighting in the pixel shader instead of the vertex shader. This slide shows a comparison of different lighting modes. On the far left, we have no lighting at all. This is the same red sphere. All of these images are the same vertices that are just lit differently. On the far left, I have no lighting at all. This is just the red color being returned, and as you can see, it doesn't have any three-dimensional look to it, because where we get the shading is what gives us that sense of depth. The next one to it is flat shaded, and that's where we do the lighting calculations, the same falling lighting calculations we just showed, but we do it on every triangle, and we consider that that triangle must be flat, and so all across that triangle has the same lighting value. That's what we're going to do in the lab for the cube. We will be doing it that way. Next over is what we call garrote shading. Now in garrote shading, that's what I just showed on the previous slides, where we do the Phong lighting calculations on every vertex, and we allow the pixel shader to just get the interpolated colors from that. We light each vertex, and then the GPU, as it rasterizes, will interpolate the colors across the triangle, and we'll just use that in our pixel shader. The last one here is labeled as Phong. This is pixel lighting. Let me stress, this is the same level of tessellation as this shape. And it's the same level of tessellation here, but here we get a very round, very smooth specular highlight. And the way we did that is because we did the Phong lighting calculations on every single pixel, not every single vertex. And that allows us to get that non-linear lighting gradient across the triangles. So what you see here with the garrote shading, this is fewer calculations because the lighting is only done on the vertices, but it creates a very, blotchy look that highlights the vertices and the triangles and sort of gives it away. If you want it to look more round, you should go with pixel lighting. One more thing I want to point out about this slide is that it calls this is labeled as Phong. We're using Phong lighting calculations for all these three last ones that have lighting. They're all done with Phong lighting. The last one is pixel lighting, and that is really typical of a modern game engine, is to use per pixel lighting like this. And the last thing I want to stress is something I have mentioned already a little bit, but I want to put a little emphasis on it, and that is you need to renormalize the normal in the pixel shader. Now, many times I will see this like, oh, I normalized the normal in my vertex shader. That should take care of it. Let me explain why that doesn't take care of it. Consider this as a three-dimensional sphere, and I want to represent that in a wireframe. I want to represent it as triangles. So here's some triangles. So a very low resolution to emphasize this. So there's some triangles that maybe represent that shape. Let's look at some normals. So we're going to draw this top triangle here, and these purple lines represent normals for those vertices. What happens then when we try to rasterize this little red pixel right there in the middle? We will calculate the normal at each of the ends, and let's say those are unit length. Then the rasterizer is going to interpolate those. It's going to interpolate them linearly, and that means this. A linear interpolation between those two vectors is this green vector that I've just drawn. Now, as you can see, the angle of that green vector is correct, but hopefully you can also tell that the green vector is a little shorter than the purple vectors are. It's no longer guaranteed to be a unit length. And so we will then in the pixel shader, we'll rerun that normalize, do a new normalize, and that'll give you the full length that it should have been to correct it for that. If you don't remember to renormalize the normal in the pixel shader, you'll get a result that looks very similar to garrote shading, because we want our lighting calculations to be non-linear. We don't want to allow that linear interpolation for the normals, or then we'll feed that into our lighting calculations and get, and again, it will show that emphasis between the sides. Okay, so that is why you renormalize the normal in the pixel shader. Okay, that's it for class number 10, lighting. We will be doing a lab on this, and it'll keep coming back as we do lighting on characters and lighting on surfaces, and we're going to use this with normal maps, and we'll keep developing it as we go along. So hopefully that helps, and we'll hit this on a lab next time.